This is an AQA GCSE Physics paper higher tier, paper 2 from June 21. The thinking and braking distance for a car vary with the speed of the car. Explain the effect of two other factors on the braking distance of a car. Do not refer to speed in your answer. Let's first of all consider the condition of the car's tyres, because if they're worn, it will reduce the friction between the car's tyres and the road, which will increase the braking distance of the car. The second thing we want to consider is the effect of the number of passengers within the car. If there are more passengers, then it means that more work will need to be done in order to stop the car. And by doing that, we've explained the effect of the other two factors. Which equation links acceleration, mass, and resultant force? Let's use this formula triangle from my auntie. So if it's in terms of force, it's mass times acceleration, which is why it's this one. The mean braking force in the car is 7,200 newtons. The car has a mass of 1,600 kilos. Find the deceleration. So we want F over M. The units are all good. So it's slowing down at a rate of 4.5 meters per second squared. Figure 1 shows how the thinking distance and braking distance for a car vary with the speed. Determine the stopping distance when the car is travelling 80 kilometers per hour. So let's draw a line up from 80. We need to add these two distances together. So let's read across here first of all. That is 15. This one's 38. That's 53 meters. Because remember, the stopping distance is the total of the braking and thinking distance. Figure 2 shows part of the braking system for the car, which equation links area of a surface, force normal to that surface, and pressure. You want FAP as your formula triangle. Let's look at it in terms of pressure. It's force over area, which is why it's this one. When the brake pedal is pressed, a force of 60 newtons is applied to the piston. Pressure in the brake fluid is 120,000 pascals. Calculate the surface area. Give your answer in standard form. Give the unit. It's worth 5 marks. Let's use that formula triangle again. We're after surface area, so we can see that that is force divided by pressure. So substitute in your values. So our answer is 0.0005. We need our answer in standard form. So that's 5 times 10 to the, count that back, 1, 2, 3, 4, minus 4. In terms of your unit, what's your unit for surface area? It's meters squared. Figure 3 shows a child on a playground toy. The springs have been elastically deformed. What is meant by the term elastically deformed? It means that it will return to its original shape once the force has been removed. A student investigated the relationship between the force applied to a spring and the extension of the spring. Describe a method the student could use to obtain the results shown in figure 4. You should include a risk assessment for one hazard. Your answer may include a diagram. I don't like drawing. I'm not going to draw. So number 1, set up a clamp with a clamp stand. After all, we'll need to hang the spring off something. Next up, hang the spring from the clamp. Use a ruler to measure the extension. of the spring with no weights attached. We add 1 newtons, 2 newtons, 3 newtons, 4 and 5. So add 1 newton weight to spring. Measure the extension. Let's repeat with all the other weights. Let's talk about a risk assessment. I mean, it's not a very dangerous experiment. Let's talk about the fact that the spring could break due to all those extra weights and ping into your eye. So what's the sensible thing to do here? Wear safety goggles. Which equation links extension E, force F and spring constant? It's this one here. Figure 4 is repeated below. Determine the spring constant of the spring. So let's use that equation, force equals spring constant times extension. Doesn't really matter which one we pick. Let's use this point here. So our extension was 0.1 meters and our force was 4. The extension was 0.1. To find K, we divide both sides by 0.1 to get a value of 40. The student concluded the extension of the spring is directly proportional to the force applied to the spring. Describe how figure 4 supports this conclusion. Yes, first of all, it's a straight line. It's a linear relationship, and crucially, for it to be directly proportional, it goes through the origin. The student repeated the investigation using a spring with a spring constant of this. Calculate the elastic potential energy of the spring when the extension of the spring was 20 centimeters. Use the physics equation sheet. So let's use this equation. We know that our spring constant is 13. We're after this value, and the extension was 20 centimeters. Let's get that into meters. Then we need to square it. Pop that into your calculator to get 0.26 joules as your answer. A main sequence star in a distant galaxy is the same size and mass as the Sun. That means it's a small star. Explain why the star is stable while it is in the main sequence stage of its life cycle. It's because the forces within it are balanced. So therefore, the gravitational force acting inwards and forces due to nuclear fusion acting outwards are balanced. Describe what will happen to the star between the main sequence stage and the end of the star's life cycle. You should include the names of the stages in the life cycle of the star. So remember, it goes from main sequence. Because it is a small star, it will swell to form a red giant rather than a red supergiant. Then it will form a white dwarf, followed by a black dwarf. Make sure you write this out in full sentences, but I'm just going to add a few extra details. So at the end of the main sequence, when it runs out of fuel, it expands to form a red giant, and then it collapses to form a white dwarf, and then cools to form a black dwarf. Figure 5 shows how the speed of galaxies moving away from the Earth varies with the distance of the galaxies from the Earth. Which galaxy would show the smallest observed change in the wavelength of visible light? Give a reason for your answer. So you're picking between A, B, C or D. It's going to be A down here. And why is that? Well, that's because it's closest to the Earth. Lenses are used to form images of objects. Figure 6 shows a concave lens forming an image of an object. So that image arrow is shorter than the object one, which means the image is smaller. The image of the object in figure 6 is upright. Yep, we can see that they're both facing upwards. Give two other words that describe the image. It's smaller. And because that image is in front of the lens, it's a virtual image. So you say it's smaller, or if you're feeling fancy, diminished, and it's a virtual image. Figure 7 shows an object near a convex lens. Complete the ray diagram to show how the image is formed. Use an arrow to represent the image. So remember, when you do this with a convex lens, we take a ray that goes and hits the lens, then it goes through that focal point here. Add an arrow, and then we need to track it back behind the lens. And then the next ray needs to pass from the top of the object straight through the middle of that lens. And again, trace it back. And where they overlap, that is where your image will be formed. Remember, your image here is virtual, it's upright, and it's enlarged. The position of an image formed by a convex lens varies with the distance between the object and the lens. Figure 8 shows the results of a student's investigation using a convex lens. Describe how the distance of the image from the lens decreases as the distance between the object and the lens increases. So let's just really describe this graph line here. You can see here that as the distance between the object and the lens increases, the distance of the image from the lens decreases, and as that distance becomes greater, it's actually that gradient is shallower there. So it's more gradual at larger object distances. The student measured the distance from the image to the lens 4 times. The distance between the object and the lens did not change. The 4 measurements were this. Calculate the uncertainty in the measurements. In order to find the uncertainty, you want to do half the range. So the range is the highest number, 2.2, minus the lowest number, divide it by 2 to get plus or minus 0.4 centimetres. Figure 9 shows a spotlight containing a convex lens. A red filter is placed in front of the spotlight. The spotlight is directed at a blue object. Explain why the blue object appears black. The red filter allows only red to be transmitted, but the blue object absorbs all colours apart from blue. So because only red is being transmitted through the filter, it's therefore absorbed by the blue object, which is why it appears black, because no colours are reflected. Ultraviolet is a type of electromagnetic wave. Give one use of ultraviolet to identify forged banknotes. You could talk about tanning lamps, but I'm going to go with the identifying forged banknotes route. An ultraviolet wave has a wavelength of 300 nanometers. Which one of the following is equal to 300 nanometers? That is times 10 to the minus 9 meters. So put that in standard form and it becomes 3 times 10 to the minus 7. The speed of ultraviolet waves is 3 times 10 to the 8 meters per second. Calculate the frequency. So this is the wave equation. Our speed is 3 times 10 to the 8. We're after frequency, and the wavelength is 3 times 10 to the minus 7. So to find f, divide both sides by 3 times 10 to the minus 7 to get 1 times 10 to the 15. Table 1 gives the wavelength of an ultraviolet wave and 3 other electromagnetic waves. Draw one line from each wave to the name of the wave. Let's just put the order of waves. So it goes radio, microwaves, infrared radiation, visible light, ultraviolet, X-rays, gamma rays. You've got your longest wavelength at this end, shortest at this end. So if we're told that ultraviolet is 300 nanometers, wave G is much longer. So we're looking at this end. The one with the longest wavelength here is infrared. So that's done. Then we want one with a slightly longer wavelength than ultraviolet, wave F. So we're looking for visible. And then it makes sense that wave E is X-rays because it has a very short wavelength. Electromagnetic waves are transverse. Some other types of waves are longitudinal. Describe the difference between transverse and longitudinal waves. So for transverse waves, vibrations occur perpendicular to the direction the wave is travelling, whereas for longitudinal waves, the vibrations occur parallel to the direction the wave is travelling. A teacher demonstrated some features of waves using a ripple tank. Figure 10 shows the ripple tank. The teacher measured the time taken for 10 wave fronts to pass the mark. The teacher repeated this measurement 3 times and calculated the mean. What is the advantage of repeating measurements and calculating a mean? Well, it allows you to gain a more accurate mean or to reduce the effect of random errors. The teacher's measurements for the time taken for 10 wave fronts to pass the mark were this. Calculate the mean frequency of the wave. Give your answer to 2 significant figures. Okay, so there's time. Frequency, remember, is given by 1 over time. What's our mean time? Well, take those 3 time values and divide them by 3 to get 8.1. Now be careful, that is the time taken for 10 wavefronts. So what is the time taken for 1 wavefront? Well, divide the answer by 10. So we're now ready to pop that into our equation. And then we want our final answer to 2 significant figures, so it's 1.2. In a different investigation, the teacher wanted to determine the speed of water waves in the ripple tank. The teacher did not measure the wavelength of the wave. Explain how the teacher could determine the speed of the wave. So speed is given by distance divided by time. So you want to measure the distance travelled by a wave using a meter ruler. Measure the time taken with a stop clock. And then use the equation speed equals distance over time to find the speed. Figure 11 shows a cyclist riding a bicycle. Force A causes the bicycle to accelerate forwards. What is the name given to force A? It's at the interface between these 2 surfaces, so it's friction. Figure 12 shows how the velocity of the cyclist changes during the short journey. Determine the distance travelled by the bike between Y and Z. Remember, we need to find the area under the graph line in order to find the distance. I'm going to break it up into A and B. So area A is 20 times by 5.4, which is 108. Area B is a triangle, so we do half times 20 times 5.4 to get 54. Add those 2 numbers together to get the total distance. So it's 162 meters. Figure 13 shows the gears on the bicycle. Describe how the force on the pedal causes a moment about the rear axle. The first thing to notice is that the force on the pedal causes a moment around the pedal axle, which therefore causes a force on the chain causing a moment on the rear axle. Figure 14 shows a different cyclist towing a trailer. The speed of the cyclist and the trailer increased uniformly from 0 to 2.4 meters per second. The cyclist travelled 0.018 kilometers whilst accelerating. Calculate the initial acceleration of the cyclist. So there's our initial speed. There's our final speed. There's our distance. And we're looking for A. So we need v squared equals u squared plus 2as. V squared is 2.4 squared plus 0 squared plus 2 times A, which is what we're after, times 18 because we need that kilometres in metres. So 5.76 equals 0 squared is 0, do 2 times 18, which is 36. And then to find A, divide both sides by 36. So our answer here is 0.16. The resultant force on the tow bar of the trailer has a horizontal component and a vertical component. Determine the magnitude and the direction of the resultant force using a vector diagram. Let's pick a sensible scale where we say 1 centimetre is the equivalent of 10 newtons. So our horizontal force is 200 newtons, so you need to draw a line which is 20 centimetres long. So measure that line, make sure it is 20 centimetres long. I'm going to struggle to do this accurately on the iPad. And then for our vertical force of 75 newtons, remember we want to draw a line that's 7.5 centimetres high. And then lastly, join those lines together to find the resultant force. You want to measure the length of that line. You should find that that line is around 21.5 centimetres long, which remember is the equivalent of around 215 newtons. And then lastly, you need to measure this angle here, which again should be around 21 degrees. And by doing that, you found your magnitude, so that would be 215 newtons, and the direction of the resultant force. A student made a moving coil loudspeaker. Figure 15 shows the diagram of the loudspeaker. Oh, I know this question is going to be about the motor effect. What is the name of the effect used by the moving coil loudspeaker to produce the sound waves? Woohoo! Motor effect. Why do I know that? Because we have an electromagnet, we have an AC supply, and we have movement. So remember Fleming's left-hand rule, which links movement, magnetic fields, and current. Explain how a moving coil loudspeaker produces a sound wave. So really we need to talk about the motor effect, but just make it very applicable to the loudspeaker. So this is the answer. You want to say there is a current in the coil of wire. Just have a look. There's that alternating current in the coil of wire, and it's going to create a temporary magnetic field around that wire. Crucially, this temporary magnetic field interacts with the permanent magnetic field around the bar magnet. A force is created which causes the speaker cone to move. And remember, it's those cone movements which cause vibrations in the air that create a sound wave. Because it's an alternating current, when that current reverses, it means that the direction of the force reverses, moving the cone the other direction. A student investigated how the loudness of a sound from a loudspeaker depends on the number of turns on the coil, the frequency of the supply. Explain why the results cannot be used to make a valid conclusion. Well, we've got two independent variables, and so therefore it's not possible to know the effect of each variable. Remember, you only ever want to change one thing at a time. A teacher demonstrated how a magnetic field can use a copper rod to accelerate. The teacher placed the copper rod on two brass rails in a magnetic field. The copper rod was able to move. Figure 16 shows the equipment used. The teacher closes the switch and the copper rod accelerates. Explain how Fleming's left-hand rule can be used to predict the direction in which the copper rod will move. Okay, so you need to get your left hand ready here. I can't really draw this. That's supposed to be your thumb. That's supposed to be your first finger, and that's supposed to be your second finger, and it's attached to your hand here. So your thumb shows the direction of the force. Your first finger shows the direction of the magnetic field. The second finger shows the direction of the current. So start by lining up your second finger, your current. That is flowing along the copper rod in this direction, so make sure your second finger is pointing this direction. Then your first finger is pointing north to south, which is showing the direction of the magnetic field. And then you should find out that your thumb is pointing to the right, meaning that the force is acting from left to right. Fleming's left-hand rule means holding, and it's as basic as this in terms of saying exactly what it is, holding your thumb, first finger, and second finger at right angles. Then we'll talk about what each one represents. Second finger equals the current. And they really want you to say which way that current is pointing, which is out of the paper. Your first finger is the magnetic field direction. Have a look, it's going to be going north to south, which means that finger will be pointing downwards. And then lastly, your thumb. Remember, it was pointing to the right, meaning that the copper rod also moves to the right. Suggest two changes to the equipment which would increase the force on the copper rod. First one is always higher current. And the second most obvious one, if you think about it being current and magnetic field going into creating that force, you want to use a stronger magnet to generate a greater magnetic field. The teacher closed the switch and the copper rod accelerated uniformly from rest for 0.15 seconds. The current in the copper rod was this. The mass of the copper rod was 4 grams. The length of copper rod in the magnetic field was 0.05 meters. The magnetic flux density was 0.3 teslas. Calculate the maximum possible velocity of the copper rod when it's left in the magnetic field. This is the equation you need, which is force on the conductor equals magnetic flux density times by current times by length. Now our end goal is to find the velocity, but we're nowhere near being able to do that yet because this equation obviously doesn't have velocity in it. However, if you remember this formula triangle here, which states that force is mass times acceleration, because we have a mass here and we'll be working out force here, we'll be able to find acceleration. And then finally, remember, acceleration is change in speed, so v minus u over t. And we have a t value and we have a u value because that's 0. So by using these three separate equations, we should end up at our final goal. So first of all, let's find our force by taking 0.3, multiplying it by 1.7, and then timesing it by the length. No need to change these units. Then we can find acceleration by doing force divided by mass. So we'll take that force value we just found, divide it by the mass, which was 4 grams, which is 0.004 kilograms, to get acceleration, which is 6.375. And then we can do this equation. We're after v. We know that u was 0, so we can just get rid of that part of the equation, and t was 0.15 seconds. So to find v, we do 6.375 times 0.15 to get v equals 0.95625. Oh my goodness, that was an awful lot of work. So to 3 sig fig, 0.956.